Welcome back to our programming language course at Riga Business School. And today we will look at a slight overview of programming language or landscape. Again, reminder, since you are taking this course, that you should have already seen the first video, right? If you go to the playlist here at the YouTube, right, you should see that there is already a video, right? So you should watch this first for the grading and a really short introduction. So now we will move on to this overview. Again, reminder again for those who have access to Ortus, again most of you already, and in fact you don't have to need access, but if you go to day one introduction, there is a link to this notebook again. Of course, you could also download this clone repository, which you already have instructions for. But again, you can download it, go directly to this notebook. The bad news is that in this course, notebooks will not be the hammer, the tool we can use for every language and every technology we look at, right? Some languages are not very well suited for notebook approach. So, but I'll still try to use notebooks since we used them before in different other courses. But okay, just for a presentation format, it's a useful format. So, again, programming languages, what are they? Again, we know we use them, right? But formally we can say these are just a means how humans interact, communicate instructions to computers. So we have our human logic and we have the machine operations, the byte code, the machine code, the zeros and ones, right? At one end, we have these machine instructions. At the high end, we have the human logic, right? So we implement algorithms, we manipulate data, create different software applications, apps, whatever you want to call them. Now, how do we want to look at this language landscape? There's many languages, thousands, literally. But there are many ways. For example, this visualization, a bubble chart of languages. What do you think is this one here? Is this by popularity? Well, let's look at the C++. Well, C++ is popular. Java is there. Are there really so many Scratch users? Well, maybe, but F Sharp and Rex, Racket, those don't really seem that popular, right? Well, and there's D also, surprisingly, right? And some languages are just outside. Well, it turns out, again, if you look at these language popularity charts, this is slightly deceptive, actually, quite a bit deceptive, because if you go to research and programming, for this particular bubble chart is formats, how many different file formats are used by a language, right, for different type of source code, right? So very misleading, right? So C++ lets you use CPP, different type of file extensions, right? So it gets to be gets top billing, right? So that's of course not even the main way of looking at it, right? For example, here we can look at a bubble word cloud of like the big languages. Again, you have to see what it says here. You got to go to link if it's still alive, actually. And of course we go here and let's see. Yeah, and this is worldwide January 25, actually, right? And so Python's still leading, right? So we're using this chart, and I think it's using Google Trends. So you get something like this, actually, right? Is this the same one? Let's double check. And I think it is the same one, right? Yeah, or maybe this is actually a previous one, actually. Right. So, but of course we know Python is big, Java is big, right? JavaScript is huge, right? C++, C#'s here, C++ somewhere here also, actually, right? It should be here. If you look at it here, it should be here somewhere, right? Yeah, because C and C++, so that's actually in this particular survey, right? Way of methodology, C and C++ are counted as one, which actually might not be the most appropriate. Actually, some people who are really hardcore C programmers, they will be very annoyed that they are counted in with C++ programmers, right? So let's again look beyond. When you see these different charts, they are at best slightly misleading, right? Because right, so TIOBE index again is the most used one. Again, still flawed. Why is it? Right, December 24, what's happening? Python still in first place, C++ second place, right? But how do they do it? Well, TIOBE uses basically mostly web searches, basically, right? So that's Google, Amazon, Wikipedia searches, right? They don't completely publish their technologies, their criteria, right? But again, you could argue that some languages which don't need much searching, right, should be higher, right? It's a popularity contest, right? Not necessarily that says what the best language is. Notice here C and C++ are different. I still don't know how they search for C language. Do they look for C lang? I don't know. They might not catch all the C language resource and searches, right? So some languages are of course easier to search for, right? So for surprisingly, for example, Visual Basic is still a big part, and Fortran, which is I think really shocking to me at least, that it's. I will not be surprised it's still a top 50, but Fortran being in top 10, I don't know. I think it's a little sus, right? So same goes for Delphi. Well, Delphi I'm less surprised about Delphi, right? So PHP, I'm not surprised at all. Scratch, because of course for learning. So again, take it with a grain of salt, right? So was this a LinkedIn? Yeah. Well, some author who does this, right? So, but let's move on to how we classify languages, right? We can do by abstraction level. That's one way of doing it. We can do a high level languages, right? Things like Python, Java, well, C++ maybe less, so JavaScript, I would say Ruby, Go, for example, relatively high language, right? Meaning, it should be easy to read for humans, right? And again, there are levels. Python, I think, is much easier to read and write than C++, right? You don't really need much documentation. You can learn it, right? And there's some even easier languages, such as Lua, for example, is even easier to write. And I would say Go also falls under this example. And you can argue some other languages as well. Now, low-level languages, which is assembly language, would be probably the closest one. You could argue that C is relatively low level, but C++ is sort of also relatively low level. How about Perl, right? Well, it's not really closer to machine code, right? But it is relatively hard for humans to read with somebody else's code, right? So readability sort of is maybe less important here than abstraction, right? How close are you to the bare metal, right? The language is fourth stack-based language, which I think is relatively low level, right? So things which approximate the computer hardware, like BrainF language, which I'm not giving you the full name, is relatively low level. It's extremely low level language. Now, you can also talk about markup language, which are not really, again, people often confuse them with programming languages. They are not programming languages. So HTML, XML, MD, Markdown, right? They are not programming languages, right? So one way of doing is C++, assembly language, machine language, and hardware, right? It's just one of the many ways of classifying, right? What's a high level language? Again, this pyramid, I would say Python goes here, Java somewhere in between, Rust somewhere above C++. Again, you can zoom in, right? You can zoom in and add more languages in there. All right, we can also classify, which we'll be doing in this course, by paradigms, right? How the language is actually described, how the language functionality is described, basically. So, for example, imperative, which is the most common, well, I would say most languages start as imperative. Basically, you write code and as instructions, basically as most computer hardware works, right? Go there, do something, jump maybe, do a little if, right? Keep doing things on sort of like a granular instruction level. Do that, do this, do that, and just keep doing it, right? Maybe you do some jumping, right? Of course, you do jumping, right? Go to a different address, do something else. Grab data from somewhere else and keep doing it, right? So that's how it's probably one of the earliest, I would say, earliest paradigms. Object-oriented, much later paradigm, 70s. Again, we'll talk about history in next lecture on Thursday. Is how do you organize code? Well, around objects. Again, we've seen this in C++ and Python. We have data and methods, and we manipulate and operate on the data. The methods operate on the data contained within. Of course, Java is a classical example, C++ as well. Now, there is also a functional approach. basic approach. The goal is to avoid changing the state, meaning something comes in, you do something, you bring something out, some data, right? But you don't mutate the data inside. What do I mean by that? You mean something comes in, right? Something close to how mathematical function is, right? It turns out like Haskell would be the most pure example, but in this course we'll look at a closure, a variation of Lisp, which is sort of a more pragmatic approach, right? So, very powerful, again, technique. Will be useful even if you don't really use a pure functional language such as Haskell. Now, declarative, basically you say what needs to be done rather than how to do it. Like a good example is SQL, structured query language, when you say what needs to be done, but you don't tell the language how to do it. Basically, language somehow, you don't know, a black box you could say. If you can remain ignorant, maybe it's not even possible for you to know exactly how it's done, but it gives you the results. Now, somewhat related is a logical type of language, which is basically based on formal logic and inferencing. Like you have these rules of logic, and it's a very interesting approach, but was used to be as a future of AI in 1980s, and it's sort of been left behind, but still used. It has some very interesting uses even today. Could be it's a supplemental language, I would say. Now, on a supplemental approach, and again, most modern useful languages are actually hybrids, right? Python, multi-paradigm language. C++, also I would say it's a multi-paradigm language because you could sort of ignore the C++ parts, the object-oriented parts. You write just regular C type of code, right? For Kotlin, I would say no, maybe less, but for example, Rust, sort of, right? Many languages have different allow other approaches, basically. Even C++, for example, has a functional approach these days now. Let's look at this little chart, maybe not so little chart, right? Just one of the many ways we could do it, right? You have declarative paradigms, more imperative paradigms, right? Maybe you don't know what kind of state you have, right? So we have markup languages, right? If you take these two concepts we've discussed previously, Turing complete languages, meaning they're all reduced to this Turing machine. We will talk about what Turing machine is if you don't remember. Now, also we talk about how the state is actually, how the knowledge is preserved, right? Name state, of course, is usually have some namings, right? Some data types, abstract data types. There's all kinds of different concepts inside. I would advise you here not to worry too much about this formal diagram, right? It's not going to be on the final because there's no final, right? But see maybe some ideas to see how we have many ways of classifying what languages do, basically. That's the main idea behind this visualization, actually. Now, yeah, this is from some of a combination of work. Now, also, next way how we can classify languages is by what do they do, what are they for, or application domain, right? Most languages, of course, are general purpose languages, right? Because they can be used for pretty much anything, right? And then you have the domain-specific languages that are used for something specific, right? Again, classical example would be SQL for query and manipulating languages. Of course, HTML and CSS also for creating web page, but it's actually not a programming language. Actually, the HTML is definitely not a programming language. CSS, funnily enough, is Turing complete, so you could technically argue that it is actually a programming language, but most sane people don't use it as a regular programming language. Latex, I would say, is used for creating static documents. It's actually a markup language, but I believe it's powerful enough to be classified also as a Turing complete language. Now, Markdown, again, not a programming language. Regular expressions, also not a programming language. Now, how about even though most languages are a general purpose, they usually have their own niche or specific use, right? So, web development, of course, JavaScript, HTML, CSS, and then you have some other backend languages such as Python, Ruby, and so on, right? Scientific computing, for example, again, notice Python appears many different places, right? But because it can do anything, right? But it is truly a general purpose language. But R here, right? I would say it's more statistical. Same goes for MATLAB, for simulations, things like that. Now let me double check if I'm recording all of this, right? I am recording, so everything is great. Now, systems programming, again, C, C++, Rust. Again, that's a big area. Game development, C#, C++, C#, Unity. Again, these are actually frameworks, of course. Now, mobile apps, Swift. You don't have really much choice these days, right? Well, you could, but for iOS Mac development, you need to use Swift. Kotlin for Android also is highly recommended these days, even though you could technically use Java or C++ for development. And of course, Dart, Flutter, which actually has some inner drama. I would probably not advise you to use it, but you can still use it, yeah. On desktop apps, and we can use some other domains, of course, right? So, languages usually, there's no, I mean, Python probably comes the closest to all-purpose language, but even still then, you don't really want to write an operating system in Python, right? So, again, like C++, you could do everything in C++, but you don't really want to do everything in C++. Same as the language, or we're going to discuss in this course, Rust. People want to do everything in Rust these days. I'll tell you, it is not a good idea to do everything in Rust. Rust is actually really good for systems programming. You could try for other things if you like it, enjoy it, but yeah. So big trends, of course. What's happening these days? Well, of course, machine learning, right? For actually generating code, right? Python is a big one here. WebAssembly is a very interesting trend, meaning you could write some languages which are not typically used for web development, actually run some languages, some maybe I would say lower level languages in a browser, right? Big data, of course, for learning, for handling large data sets. Again, it often goes together with machine learning, but not necessarily. Concurrency, of course, that's another big one for last 10-15 years for sure. Is that most of our computers have multiple cores, right? If you have less than 2 cores in your computer, I think you are in trouble. But I mean, well, most computers these days have at least 4 cores or more, actually, right? 8 and 16 are almost not quite common. Now, again, we see, of course, the explosion in storage capacity. Again, languages deal with large data, of course, are quite important. Now, learning curve, another aspect of how you would discuss how would you choose a language. Python, great language for learning, but you still use it. But as you saw, most of you saw in the previous course, C++, well, I'd say it's a little bit harder to learn. Again, some people who took some colleges and some universities teach you C as a first language. I'd say it's probably, again, sort of like letting you swim before you actually know how to, throwing you in the water before you know how to swim, I would say. But yeah, there's some pros and cons for that approach as well. Now, another thing you should discuss, of course, should consider when choosing a language is community and ecosystem. That's where I'd say academic courses, well, they're academic, right? Just like this course is mostly academic. As much as I want to keep it, you keep some practical information, right? Pragmatic information. There is this community and ecosystem is very important, right? So Python, for example, is so popular because it's already popular, because there's helpful community and a huge ecosystem. Some languages actually cultivate this elitist approach, which I personally am not a big fan of, because they say, okay, if you're not doing it, they say you're doing it wrong, right? There's might be maybe slightly, how to say, I would say snobbish, right? Not helpful for language growth, right? But strong community is not the only reason why some languages are more popular than others, right? But good documentation, extra third-party resources, right? Community itself is very important when choosing a language. So, for example, this is at the time of, I don't know if NVIDIA is the most valuable company in the world, or at least second or top 3 company, market value over 3 trillion at least, if I remember correctly. Have not checked the stock price in the last few days, but it basically is because it built this CUDA, C-U-D-A, ecosystem around C++ for GPU programming, meaning basically for writing on NVIDIA graphical processing units or graphical cards, if you want to say it, or not really cards, well, units, right? It includes helpful libraries, and NVIDIA has really cultivated this approach as opposed to other companies such as AMD and Intel, for example, right? I'm throwing stones in their fields right now. They have not done so well in this regard. So now, on by providing these helpful libraries, these integrations, it's played a really big part of why CUDA ecosystem has won. Basically, at the moment, it's a huge moat for basically everybody's using it because it is easier. It is easier, right? So it expands, right, to extends to support a specific application domain, right? So libraries, data centers, right? It works very well together. Now, so future outlook, of course, languages. You could even learn, make your own language, right? Again, for fun. We'll have some tooling in this course to learn, do so. But again, there's future outlook. Like Rust is, of course, because that's you're going to be looking at this course. It's quite important. Like this course, one language I would like to include, maybe in some future, maybe Julia is interesting language, but again, I'd say it's really a domain-specific language, so useful for scientific computing. So also I like NIM, for example. Had some students who have written some papers on it. It is a good sort of like in between Python and C. Again, something for you. So these languages like Julia and NIM, if you want to write an optional report on them, I would love to see it, right? So again, how do you evaluate programming language features? You want clarity when you do readability. Is it clear? Is it simple, right? Because when you are writing code, you don't really want to keep too much information in your head, right? Cognitive load, it's a real issue. Do you want to juggle the syntax, right? Do you want to know, okay, there are 5 ways to print something, right, on the screen, right? Which way how do you format this, right? And do you really want to learn this, right? All of it, keep this in your head. No, you don't really want to do this usually, right? Is it consistent, right? And remember, all of these 3 things, every language will have its weaknesses and strengths. Same goes for writability, right? How can you write complex algorithms and data manipulations? Some languages are very primitive. Actually, for example, Go. We will look at the Go language. It is relatively primitive, right? You can write complex things, but it's concise. Some languages are really concise, right? But again, some languages are too concise because you don't want to sacrifice readability. Now, flexibility. Does language allow you for multiple paradigms or approaches? Is it procedural? Like, can you do multiple things? Like, can you do it like in Python or C++? Can you use different approaches? If you use Java, all you can do is object-oriented approach, right? So, again, efficiency. Another important consideration, because as we will know, compile language tend to be faster, right? Resource utilization. Again, some languages, hello world, will take you 100 megabytes. Well, these days maybe not a big deal, but some languages only take maybe 50 kilobytes. Much better. If hello world takes 2 gigabytes, probably not what you want to use. Maybe there's it could be some sort of big library. I don't know what language could probably some framework maybe, but that's probably not the language you want to use at the moment. Now, safety, right? How well does the language? What kind of safeguard does the language put on your code writing? Right? Type errors, very common. When do you catch them? Do you catch them when you compile something? Compile language will generally catch these errors, right? Or do you do it at runtime? Python or JavaScript, you run a program and it crashes maybe at some point, right? You don't know it's going to crash. How do you do exceptions? Do you actually have exceptions, right? There are different methods of doing that. Memory safety, right? How do you deal with our friend buffer overflow or memory leaks, right? Do you protect them, right? Also, libraries and frameworks. Now we move on to extensibility and modularity. Is there good standard library? Is there standard library? Are there good third-party libraries, right? Is there an easy way to do modules, right? Imports. How do you organize it? Are there plugins, right? Do you extend it? Maybe it's possible, maybe it's not needed, right? Maybe modules are enough. Also, again, I mentioned like community, right? Job market. Well, that anybody is hiring in this again. Again, that might be an important consideration. Some languages are just fun to learn just for heck of it, right? Sometimes they lead to actually good jobs, right? But maybe, that's certainly an important consideration, right? Maybe there's some special things, right? For example, linking C plus C sharp for data manipulation, list comprehensions, right? Is there a meta programming? Very cool thing. You can write code that generates or modifies other code, right? Is that possible actually? Some languages don't let you do it. Some are very, very flexible in this regard. Portability, another consideration, right? Do you want to actually run it on different systems, or are you fine with being it only, for example, Swift, mostly macOS, right? So web compatibility, is this actually used for web development? Maybe completely not needed for your use case, but maybe this is an important consideration, right? Also, is it backwards compatible, right? Again, this is something we skip on sometimes. Like, is Python, again, I'll give Python as an example, Python 2 to Python 3, very painful migration. Many, many languages such as Perl had this problem, PHP even somewhat, right? Many, many languages have this problem that at some point the backward compatibility, well, inevitably fails, right? How do you deal with it, right? I would say C is pretty decent in this regard, right? Interoperability, can you use other languages? Can your language embed other language, or can your language be embedded in other language? For example, Lua is famous for being easily embedded in other programming languages, as sort of like for scripting, for live scripting, for example, just a use. Now, so again, remember, now let's go back to our basics. The programming languages are used to be used with computers, so you should now just have a basic idea how computers work, right? Hardware level, right? Most common hardware architecture is still von Neumann architecture, right? The idea is this: you have memory, you have a CPU, and again we'll skip the part there's GPU and things like that. Let's call it CPU for now, right? You have some input, output, and you have some bus which transfers data. The big idea is this part here: stored program concept. Data and program instructions are stored in the same memory. This means that programs can be loaded into memory for execution, and it can also be modified even during runtime, right? So typically instructions are sequential, right? One at a time. Of course, modern implementations include pipelines, multiple cores, things like for parallelism, right, to improve performance. But the big abstraction is to think of it as sequential instructions, like a big list of instructions, right? There might be a program counter. It could be mutable state, of course, right, because data usually are mutable. Now, during the years, this architecture has been extended and modified. It's still von Neumann, but there's of course caching, there's pipelines, there's multiple cores, specialized processors such as GPUs, TPUs, right? This is actually using TPU. No, it's GPU. Google Mute Engine, but I think it's just TPU, just regular CPU here. Right. So, but they generally operate alongside von Neumann based CPUs. Right. Basically, there's something called von Neumann bottleneck, where speed of operation is limited by the rate of which data can be moved between CPU and memory. This is increasingly a concern these days, right? Basically, the memory can keep up with how fast CPU is running, right? But von Neumann stays the same. So this is the basic idea how it works. Now, so how does the programming language do it, right? There are a couple of ways of doing it. Interpreted languages, well, we execute code line by line, right? Python, Ruby, JavaScript, and so on. Again, of course, underneath there could be some other variations, right? Interpreted languages, classical. But the problem is, of course, that this interpretation step adds extra layer. There's memory inefficiency, and, well, if you look at the language speed tests, benchmarks, these are the slowest languages, right? How about compiled language? C++ is a good example, right? Usually you get a file. You compile the code and you get executable file, right? So, faster, could be optimized, right? More control, closer to hardware. But the problem is, of course, you have the compilation speed. If you want to compile some bigger program in C++, it could take, couple, I don't know, long time, right? Let's do xkcd compiling, right? Old comic, right? Here, and if you check it, right, my code's compiling. A good excuse if you actually, right, want to go take a coffee break, right? But actually it is possibly, right? You can compile like Linux kernel, I think in an hour could be, depending on machine, right? Like Firefox could take a while to compile, things like that. Like some big projects could take a while to compile. Now, what's interesting is usually there is a sort of hybrid approach called something just-in-time compiled languages, meaning it's interpreted, compiled to bytecode, right, then dynamically compiled to machine code just before execution, right? And again, there's a big variation between these, right? So Java, C Sharp, right, and some versions of Python, JavaScript, right? There is this initial step, add some latency, right? There also needs memory usage, right? But also much more complex, but it is faster actually, right? So there's a here hybrid approach, interpretation, just-in-time compilation, right? So there are different versions of language, could be the same, but it could be different implementations. Now let's talk about why we are here, right? You survived this introduction, this overview, but and why should you, if you don't plan to make a new language, right? Why should you study this course, actually, right? Maybe we should have started here. Well, you learn by learning other languages, you will improve your tool set. That's a basic approach, right? As I don't know, your grandpa said, variety is spice of life, right? By seeing different approaches, just like you should travel around the world, right? You should also study different language to see how different approaches, because then you'll have a wider tool set again. Otherwise, if you have a single hammer, you will be hammering, you have a screw and you will be using a hammer to hammer in a screw in a wall, which is probably not what you want, right? So now you will learn also some different approach to debugging and troubleshooting. You broaden your problem solving skills, and hopefully your code quality in your your main language will improve, right? And again, it's mostly about informed tool choice. Also, even if you don't want to be a programmer yourself, if you'll be inevitably working in teams, maybe leading a team, where there will be technical discussions, and if you have this sort of knowledge of these approach, even Steve Jobs, who famously was not a programmer, right? He did have a good sort of high level understanding of multiple programming languages, actually, right? It's kind of interesting. Now, of course, there are other languages. Bill Gates or Steve Wozniak, of course, were actually programmers, right? So now, so even if you're completely think, okay, you're going to be a business person, still it will be no useful to know about these different language approaches, right? Again, of course, also adaptability. Languages evolve, right? So once you know 4 or 5 different languages, it's very easy to learn a new one, just like a human language, right? So, and of course, it's just for fun, right? That's what school is for, right? So maybe think about what's your favorite language. This we will usually do in a class. Unfortunately, we are not in a class today, right? This is something for you to sort of sleep on before Thursday, right? Again, some concepts. And again, so what should you do before Thursday? We are going to meet on Thursday. You should do the quiz for today, right? Day 1. Right, you should, of course, see this first video, right? And do the quiz, and I will see you on Thursday when we will look at history, right? Of programming languages in general. Thank you. I'll see you then.